So as you mentioned, my main like field of research is linear dynamics, which is a subfield of functional analysis and operator theory. So I mean, it's well known that shift operators are pretty important. It's a very important class to test theorems or to find counterexamples there. So I would like to present like a history over the shifts and some recent generalizations that we are getting to improve this this class of operators and to enlarge it, to generalize it. So this is it runs over several joint works with Karl Grosse-Erdmann from Belgium, University of Mons, with Quentin Menet, again from the same university in Belgium, and with a recent one with Anton Baranov and Andrei Lishanskii from the Euler Institute of Mathematics in St. Petersburg. Okay, so a brief introduction, like a motivation. I'm going to mention notions that I didn't define yet, but just to motivate a bit the speech, is that among others in linear dynamics, the weighted shifts, they have at least two very important purposes. So one is to distinguish different dynamical notions. Like, I mean, for instance, we can find a shift which is hypercyclic and not mixing, whatever those notions are. Or we can find, this is a very difficult construction by Yard and Griveau, a frequently hypercyclic shift, which is non-chaotic, for instance. Or we can find the mixing but non-chaotic shift. But still, there are some drawbacks there. So there are some things that the shifts cannot distinguish. For instance, hypercyclicity and weak mixing, they cannot distinguish. Some other things is that the invariant subspace problem, this celebrated famous problem, has a solution, at least for the L1 or for Banach spaces, but using those read type operators, which are far from being shifts. So our purpose is to try to generalize and to enlarge this class of operators, the weighted shifts, in such a way that we distinguish more such notions, we get more counterexamples to distinguish the different, the various dynamical notions, but still we are close enough to the shifts so that we can enjoy some of the good characteristics that the usual shifts have. Okay, so this is the motivational introduction, and let me start now. I will try to restrict myself as much as possible to fewer dynamical notions so that we can dig a bit deeper inside instead of overwhelming you with many definitions. So the first definition is the main definition in linear dynamics. It's the one of hypercyclicity, and it originates, it's a generalization of the well-known notion of cyclicity. So we have this first definition. Let's say that X is a Banach space. Okay, this is not important. We could take X to be a Freset space so that we include spaces of analytic functions or whatever. But for this talk, Banach space is enough. We take an operator T, which is linear and bounded on X. And this operator is called hypercyclic. If there exists a vector X from the space whose orbit, which we denote like that, and it is by definition the set, take the vector X, take the operator acting on the vector, take the operator acting on the image of the vector. So by square, we mean not multiplication, but composition, etc., is dense in the space. So hypercyclicity means that we have one vector in the space that has a dense orbit. And the name comes from a strong notion of cyclicity, which means that the span of this orbit is dense, the cyclicity. So it's natural to name it like that. Okay, and the second notion that I will define, which is related to hypercyclicity, and I'm going to stop with the dynamical notions there, is the one of weak mixing. So T is weakly mixing.
Dimitrios, problem with writing your document, not maybe in my computer. I cannot see your writing documents. They're very small.
What is it? It's very small.
Yeah.
Ah, okay. Okay.
Maybe
this slide, make it larger.
Some happens maybe in my computer. I don't know, because first time
it's okay for me.
Yeah.
I think it is your computer's problem because on my computer I see it clearly.
Okay.
So probably you can zoom in your computer and see a more enlarged version of my
Okay, sure.
Okay.
I will maybe.
So an operator is weakly mixing, provided if we consider T direct sum with T. So this is the product space. So by this symbol, we mean that the vector, the operator acts coordinate-wise. T of x, T of y. Just apply the operator on each coordinate. If it happens that this direct sum of operator T with itself is hypercyclic, then the initial operator is called weakly mixing, sorry. And it's pretty clear that if we have an operator which is weakly mixing, so if I denote it a bit like that, abbreviate, weak mixing implies hypercyclicity. Of course, because if the direct sum is hypercyclic, then on each coordinate you will have denseness of orbits. You will have such a vector, a pair that is having a dense orbit, which means that if you project on the coordinates, you will have vectors with dense orbits. So weak mixing is stronger than hypercyclicity. The inverse problem took quite a while to solve, and it seemed much more difficult. Someone would believe that hypercyclicity is weaker than weakly mixing, but the counterexample to be found was extremely difficult, and even by now we have only one such counterexample, which comes from De La Rosa and Reed. So this is a highly non-trivial example, extremely difficult, and it's the only one that we have to distinguish those two notions. So weak mixing is not the same as strictly stronger than hypercyclicity, just by this example. Okay.
I'm too much sorry. Can we have, before passing to the next slide, just give one simple example of that hypercyclic operator? Thank you.
Yes, I was planning, because okay, some simple examples is, I will give a much more general, but some simple examples. We can take 2 times the backward shift on L2. More generally, we can take lambda times the backward shift on L2, provided the absolute value of lambda is bigger than 1. Another counterexample, not on the Banach space, on the Freset space, but which is very common, is the differentiation operator on h of c of entire functions. This is also hypercyclic. So many natural operators have this property. It's not something very rare and difficult to find. It occurs pretty much naturally to many natural operators. But we will see at least the 2 times backward shift and the lambda times the backward shift. We'll see much more general situation on weighted shifts on the LP spaces. Okay, so the next thing that I would like to mention is, this is just to build our intuition. We will not use this theorem, but we will see a generalized version of it for more general shifts. So I'd like just to mention what this weak mixing is equivalent to. No, actually 2 theorems. The first we will use. Weak mixing is weakly mixing if and only if it satisfies the so-called hypercyclicity criterion. So that means that there exist 2 dense sets x0 and y0 subsets of x. There exists one subsequence nk, irrelevant of the dense sets, and there exist maps S and K, a sequence of maps which act from y0 to x with a property. And I noticed that those maps S and K, they don't have to be linear, they don't have to be continuous, just maps from these dense subsets subset y0 to x, such that three properties are satisfied. The first one is that T and K of x goes to 0 for each x on the first dense set. The second one, S and K of y goes to 0 for each y on the second dense set. The third is that T and K of S and K of y converges to y for each y in y0. Okay, let's pause for a second to understand what this means. So T is weakly mixing if and only if one can find two dense subsets so that many orbits go to 0 under T. The second one and the third one means that we have approximate right inverses that converge to 0. This is what it means. Okay, you don't have an exact right inverse, but you have something converging to a right inverse, which should be very small. We have a smaller remark here, which is not difficult to show, but it's not also trivial to show in one line, but that provided if T is weakly mixing, so that means that equivalently it satisfies this criterion, then those approximate right inverses can be defined everywhere on the space. So we can take S and K be from X to X. So they don't have to be densely defined, exactly because of this approximating. You have to converge to a right inverse, so you can extend on neighborhoods of points and you can define them everywhere. Okay, so this is one thing. And the other thing that I meant to say, so this is important, this we will use later on, and this is the main tool of proving hypercyclicity, pretty much. So one proves that the operator is weakly mixing always, apart from this one result of De La Rosa and Reed, which is extremely difficult to construct. And the operator is hypercyclic, but doesn't satisfy this hypercyclicity criterion. Okay, so the other characterization in terms of neighborhoods, if we want to see, of weak mixing, is weakly mixing, provided if and only if for each U, V subsets of X open, for each W a 0 neighborhood, there exists one time n common, such that En of U intersect W and E and W intersects V. So this means that we have one set U, one set V, and another one 0 neighborhood W. We have to satisfy for the operator to be weakly mixing that for the same time this comes here and this goes there. In other words, saying schematically somehow, the operator to be weakly mixing, it has to be that something big becomes something small and something small becomes big after the same time, synchronized. So the fact that this is equivalent to the hypercyclicity criterion is highly non-trivial. It's slightly difficult. One implication is easy. The hypercyclicity criterion implies this neighborhood definition. But to go from this back to the hypercyclicity criterion takes more work. But I just wanted to mention this because it will occur in the very end of the talk. So, I mean, to summarize, up to now, for weak mixing, we need a big part of weak mixing is small right inverses. This is something that we have to keep in mind because it will help us. Now, let's pass to the concrete examples that, I mean, the unilateral weighted shifts on the normal LP or C0 spaces. This is the first example to see, and it's the motivation of everything, of all the rest of the examples. So unilateral weighted shifts. Of course, we have also the bilateral shifts, but this I will leave totally outside of this talk. It becomes a bit more technical, and I think that as a first talk, it's better to keep things as we deal. We always deal first with the unilateral case, and then we extend to the bilateral. So the spaces, first of all, are either LP for P bigger than or equal to 1 less than infinity, or C0. Natural question, why do you leave L infinity outside? And the problem is that hypercyclicity happens only on separable spaces. Of course, you demand an orbit, which is countable, to be dense. So the space, if I mean, it would be better if the space was separable in order to have any chance to support a hypercyclic operator. So L infinity is not separable, so we just throw it out. And the substitute of L infinity is this C0, which is a closed subspace, which is separable. And then we take a Wn sequence, and we define formally, I'm not putting any restriction on Wn just for the definition, Bw of a sequence, and then start indexing from 0, x0, x1, x2, etc. Be W1, x1, W2, x2, W3, x3, etc. So for each slot, we multiply with a corresponding weight, and then we shift backwards. The first index, the first coordinate is getting dropped outside. So yeah, it's mapped to 0, or the elements with only first coordinate non-zero. Now we have that the operator, this is a very simple exercise to check, it's almost immediately, is well defined and bounded. Those two are equivalent actually by the closed graph theorem, if and only if the weight sequence W is bounded. And intuitively, it makes sense. If you want the lengths, the magnitudes under the operator not to grow too much, you have, and it's if and only if, the W to be, the weight W to be bounded, so that you enlarge up to a certain amount. Okay, and now the theorem that characterized hypercyclicity and weak mixing for those kind of shifts came by Salas. It was published in the transactions of the AMS. And states that if W is an L infinity sequence, so that the operator is bounded, then the following are equivalent. The first is that BW is hypercyclic. The second is that BW is weakly mixing. And the third is that the supremum of the absolute values of weights W1 up to Wn is infinity. Okay, so for that's why I was saying that 2 times the backward shift is a very particular case of this, in which case the third condition is satisfied trivially because we are getting 2 to the n. So this product becomes 2 to the n, and of course it goes to infinity, and lambda b satisfies the third condition, provided the magnitude of lambda is bigger than 1, because again, you will get lambda to the n on the third condition. So this is much more general. The comment is that, of course, we have hypercyclicity equivalent weak mixing. We would expect that, because I mean, anyway, it's very difficult to distinguish those two notions. And I would like just to prove 3 implies 2, that this condition implies that BW is weakly mixing. Because this is what we will need for later on to for our work somehow. And before doing that, okay, let me start a new page. So for the proof, 3 implies 2. I would like you to believe me, and I can say 2 words about this, that 3 is equivalent to saying that there is one subsequence nk such that for each j bigger than 1, if you start wj plus 1 up to wj plus nk, this goes to 0. Of course, what I wrote here is stronger than 3. 3 implies one subsequence, so that if you start multiplying from w1 up to wnk, you go to infinity. But then, okay, the first few terms don't change the behavior of a sequence going to infinity. You just, I mean, this is a scalar multiple difference. So you can drop the first few terms, the first j terms. This is not a problem. The problem is how to vary the final index from nk to nk plus j. And just the idea and the structure here is non-trivial, but it's not difficult to show, is that first you go backwards from nk to nk minus 1 to nk minus 2, etc., preserving this property just by the fact that the operator is bounded, just by the fact that wn is bounded as a sequence. So you can go backwards, and then you just relabel the subsequence. So instead of going to nk, you go to the first one and then you increase. That's the idea pretty much. But anyway, it's slightly technical. It's not giving us so much something for the rest of the talk. So I'm just asking you to believe that 3 is equivalent to that. And now, believing this as an assumption, to prove weak mixing, we're going to apply the hypercyclicity criterion. And this, from now on, this part becomes very common in all the generalizations. So that's why I wanted to stick to it and to show it. So for the hypercyclicity criterion, first of all, we needed one subsequence, which is going to be this subsequence, nk, provided by the assumption. We needed 2 dense subsets. Usually those dense subsets, we take, so x0 to be equal to y0 to be c00, the finitely supported sequences. And why is that? Because, I mean, the first condition that the iterates have to go to 0 is trivially satisfied for the unilateral shift. If you have a finitely supported sequence, you start shifting, so you start dropping terms by terms out. And if the sequence is finitely supported, after a while, you will have dropped all the support outside. So it will be mapped actually to 0. It's not going to just converge to 0. It is going to become 0 after a while. So, yeah, the first thing is that T and K of X equals 0 for K large. And for each X in C00, that's trivial. Now, the second part is how to define those approximate right inverses. So we want to define those S and K that we said before. We want to define those on C00. What we will do, and what we will do in the rest, actually, is that we will define them on the basic vectors and then extend them linearly. They don't have to be, but sometimes it serves us. So by just taking one EJ, I want to make sense of this S and K of EJ to define this thing. And this thing, I'm doing the reasonable thing. I want a right inverse of EJ. So I want to define something so that if I applied nk times the operator to go back to EJ, that means that I have to shift forward, and instead of multiply with a weight, to divide by the corresponding weights. I'm just undoing the effect of the operator. So I'm doing 1 divided by W, J plus 1, all the way up to J plus nk, Ej plus nk. This is exactly what you need in order, if you apply the operator, slowly you will cancel out all the weights and you will go back to Ej. So you shift forward and you divide by the weights. And now this goes to 0 as k goes to infinity by the assumption that the weights in absolute value go to infinity. And this happens for each j. So this extends to the linear span of them. So you get C00. And of course, you have that E and k of S and k of y is actually equal to y for each y finitely supported sequence. Also, this is satisfied. Hence, the hypercyclicity criterion is satisfied, so T is weakly mixing, where T is the backward shift. It was EW. Okay, and the proof was pretty much easy, assuming this that the condition 3 is equivalent to this a bit stronger condition. But I would like to do some remarks here on this characterization. Let me go back one page. So BW is hypercyclic, weakly mixing, if and only if this condition is satisfied. This condition doesn't depend on P, which is a bit strange. So I mean, we have a class of operators on all those bases LP or C0, and they are either all together hypercyclic and weakly mixing, or they are not. So the space doesn't make a difference on the condition. We would like to define some class of shifts which is a bit more delicate there, which can capture the difference from a space to another. The other thing that I would like to comment a bit is that when it came to define this right inverse and we wanted those approximate small right inverses, we didn't have actually a choice. So, okay, I mean, if you don't define it like that, it's essentially unique, the definition of the right inverse. I mean, you can put some elements here and there on other slots and just perturb it a bit, but you're not doing something. Actually, you're even enlarging the norm of the right inverse, and you're not offering something, you're not helping yourself. So the essential part of the definition of the right inverse is unique. the operator shifts, the operator T shifts forward to the left and multiplying by the weights, so the right inverse shifts to the right and dividing by the weights. That's unique. You have one line that you are moving either to the left or to the right. That's it. This we will not have in the future. And the third thing is that all those backward shifts, they are acting on sequences which are indexed by the natural numbers. And this is essential on this left-right thing and uniqueness of the right inverses. Now, what we will try to do is the first generalization to substitute this set of indices, which is the natural numbers for the unilateral case, with a rooted tree. So we will start taking sequences over a rooted tree and shifting over the tree. So the indices are going to become a tree. Okay. Now we have weighted shifts on trees. Few preliminary stuff. I'm pretty sure that you know the notion, but just to be on the same page, I will very fast. I don't want to spend so much time on the graph theoretic part, but just to define a bit what we mean by tree. A rooted tree. I want to have a root so that it corresponds to the unilateral case. So we mean in a graph V, E, and this stands for vertices, and this for edges. So we have few vertices that are connected by edges, and we want it to be connected. So that means that if you have one vertex here and one there, you can always find a path directed or not going from V to U. You may have to undo some. So if you take U and U prime here, okay, you cannot find a directed path, but you can go back to V and then probably come here. If you want such a notion of connectedness, you want no cycles. So you don't want to go from V to U and then at some point to go back to V. So you go one direction. And you want that for each V vertex, there is a unique W, or there is at most, I should say, but I mean, yeah, there is a unique W so that WV is an edge. So for each vertex V, there is exactly one W that goes to V. If there isn't, this will happen only once for the root. So if not, then V equals the root of the tree. And it's unique. This we can prove. So only one vertex will not have an incoming vector. So the trees look something like that, and they keep going. We take infinite trees. Yeah. A bit of notation for this W here. We'll call W the parent V. Iteratively, we will define the parent of n degree of a vertex, provided it exists. Because if you overpass the root, it doesn't exist. But provided it exists, we will use this notation, parent of n degree. And similarly, we will call V that it belongs to the children of W, in this case above. And again, we will define the children of n degree of W to be the children of the children of the children n times. So this set of the children of n degree. And finally, the last thing that I'm going to, as a notation, is that V is called leaf if the children of V are the empty set. So if the tree goes and at some point it reaches a vertex V and then it stops and it doesn't reproduce further on from there, this V is called a leaf. Okay, so we are done with the graph theoretic part. That's pretty much, just keep the idea, the intuitive idea that you have about trees, and it's enough for this talk. We don't need something very technical or specific. Now we need the spaces. So before this corresponds to the natural numbers up to now. But then we had those LP and C0 spaces defined on like being sequences indexed by the natural numbers. So now we want to do the same for the trees. And actually here, for the spaces, V can be just countable set. We don't even need a tree structure for this. So we will just very naturally define LP of V to be the set of all sequences FV with V, the set V, capital V, sorry, such that this becomes a norm, the norm P of X, and the C0 similarly is going to be the set of all sequences FV parameterized by this countable set V, such that for each epsilon there is a finite set F, such that the absolute value of F of V is less than epsilon outside F. Normal definitions as we would expect them. So we have those sequence spaces and they are behaving as we would like them to behave. They are separable and they are Banach spaces and everything. Now, the interesting thing is how to define the backward shift. The tree. First, we need some weights. So let's call lambda a weight sequence parameterized by the tree. So now in our mind, we have a tree. Some children could be infinite in number. And we want to give meaning to this B lambda of, so F is going to be a function, a sequence defined on the tree. So the index is V and it spits out like a real or complex values. So we want to give meaning to this B lambda of F, and this has to be another sequence on the tree. So let's see what should do on the vertex V. So let's concentrate here on just one vertex. We have V and we have the children of V, which are U. So what we would like in the past, what we did, we had only one child on the natural numbers. We multiplied by weight and we shifted backwards. So now we want to multiply the child lambda U. So the entry of F at U, we want to multiply it with a corresponding weight, but then we have many of them. So it's natural to sum them up. So I think that this is the natural way to define, at least formally, what a shift means on a tree. You multiply the children with a corresponding weight, you shift them backwards, but on the vertex V, you got many of them, so you sum them up. You take something like a weighted average or something there. Okay, and then, of course, we have all these questions about boundedness and well-definedness, because we didn't discuss anything about that. And the theorem that we got with Karl Grosse-Erdmann was, okay, so B lambda well-defined LP of the tree or C0 of the tree, if and only if P lambda is bounded, if and only if. Okay, again, I would like to stop here to try to guess the condition. If we check how this B lambda acts on the sequence F, but like just focusing on one vertex V, it acts like a linear functional. So those lambda U's multiply the, like, let's say that F originally belongs to an LP of the tree. LP of the tree means in particular LP of the children of V. So if we restrict the sequences that are LP just on the children of V, those are, like, I mean, a subset of all the sequences of LP of the tree. And then how B lambda acts on those sequences, it acts like a linear functional. So it makes sense that we want the norm of LU, where U belongs just at the children of V, but the norm Q, where Q is the dual, to be bounded, for the lengths not to grow so much. But actually, because if you do it just here, but then the tree keeps going and you have many such functionals, if those norms keep increasing, still you will have an unbounded operator. So actually you want the supremum of all those Q norms where V runs over the tree V to be finite. This is not difficult to show. I mean, we can use the Helder inequality and show it. I just feel that it's always better to see things a bit intuitively and to expect why this condition is reasonable, why the Q norm appears here, where we want the supremum of all those Q norms to be finite. Okay, so that's the condition that characterizes well-definiteness and boundedness of the backward shift. Okay, having that in mind, we can now discuss about hypercyclicity or weak mixing, I mean, dynamical properties. We know when those operators are bounded, we will assume it from now on, and then we want to discuss about hypercyclicity. One first observation, like a tiny remark, is that if the tree V has a leaf, no B lambda, no backward shift can be hypercyclic. This is, so you have the tree going and then at some point it stops here. So the rest keeps going. So V is a leaf, it doesn't have children. Then what happens? For each F, on each space, LP or C0, let me write in X, by X meaning LP or C0 of the tree. If we take B lambda of F at V, that was given by this summation of the products times the F at the children, but here we don't have any children, so this summation is summation over an empty set, so this is 0. And actually the same thing happens for each n iterate. So if all the iterates have 0 at this V, that means that, of course, no orbit can be dense. In the end, in the best case scenario, you will approximate all the sequences that have 0 at this slot. So you don't really approximate all the sequences on LP or C0 of the tree. So from now on, we will start assuming that all the trees that we are considering are leafless, as we say, they don't have leaves. And then the second thing that we want is those small right inverses that we were saying. So at some point, let's say that we fix an n, which is a natural number, and we want to find an nth right inverse. So a right inverse, an approximate right inverse, probably for the nth iterate of the operator. This is what the hypercyclicity criterion was asking. Because again, the orbit's going to 0 on a dense set, this will be pretty much easy. We will take finitely supported sequences and we will start shifting back. And at some point, we will drop the support outside of the tree. And again, we will get it pretty much for free. So this is not a problem. The problem is those approximate right inverses. This is always the most difficult part of the hypercyclicity criterion. So now we will have a vertex V, let's say. And again, as before, we will want to approximate the vector EV. Because if we approximated, if we found the right inverse for this vector EV, then for the span, we expand by linearity those maps, and it's going to work. It's going to be fine, as we did before. And if we want to find the right inverse for Tn, so we are thinking of the operator, not Tn, but probably B lambda to the n. What happens? I'm just now speaking. We have the children of n generation of V. And this is exactly, those are the things that are going to bring some input to V after n steps. We don't care about the rest of the tree. So what will come after n steps of applying the operator B lambda to the vertex V will come only for the children, from the children of n degree of V. This is what we want. But here we may have many, we may have even infinitely many children. In the previous case of the unilateral shift, we had only one child, of nth degree, because it was just the natural numbers. So it was linear, the problem. So now we want to find what inputs to put here in such a way that this right inverse will come back the operator. So what we want is this operator, B lambda, is going to multiply with some weights, products of weights, and sum them up in the end. So we want all these product of weights and summation to add up to 1 to the unit, because we want to approximate the unit vector there. And we want the norms to be as small as possible, so that we will have a chance to be going to 0. Again, the philosophy here is that I can find some right inverse. I can just use the first element there and put, like, undo the product of weights just linearly, as if it was linear. Undo the product of weights and put all the unit, all the mass there, like, I mean, on the first side, let's say. Then I will get a right inverse, and I can demand this right inverse to go to 0. This will give me the hypercyclicity criterion, and I'm going to get the sufficient condition for hypercyclicity and weak mixing. But I'm not going to be close to get a characterization. So what we are trying to do here, we're trying to understand as delicately as possible the situation, so that we will get a characterization. So we want to get something like the best right inverse. So we want to put things here on the children of n degree in the most economical way to get the minimum P norm that sum up, that we are undoing the operator. So they sum up, and after multiplying with the weights to the unit, but they have minimal norm. Okay, so all this informal conversation leads us to the following optimization problem. I have written it from before, but I mean, all this discussion is to motivate why I'm taking all this. So essentially, we have one point and we have a countable set, I. And let's say that we have some weights, lambda I, which are even positive. We don't mind. I mean, the sign is not important there. What we want to solve, we want to solve the following, like, optimization problem. We want to minimize the norm of xi's, the P norm, with the restriction that the summation of lambda I xi equals to 1. This is exactly what we had before, with I being substituted with the children of n degree, and okay, the lambda i's are going to be some products of weights over the branches, but still there are some weights. So this is the optimization problem that we want to solve. Minimize P norm under the condition that after multiplying with some weights and summing up, you get the unit. If we made it to optimize, to solve this in an optimal way, then by demanding this quantity to go to 0, we find the best right inverses, and those going to 0 will give us a characterization of hypercyclicity or weak mixing. And this, if one does like Lagrange multipliers, for instance, calculus, or we are doing in the paper, like, I mean, the reverse Helder inequality. So there are a couple of ways to approach this, and it's not even difficult to do this, to solve this optimization problem. You get that this optimal minimum norm is 1 divided by norm lambda I Q, the dual. Where, as usually, of course, if P is 1, then Q is infinity. If P is infinity, Q is 1. So yeah. And the minimizing vectors, the minimizers, are the vectors xi. So which quantities to put at the I to minimize? Those quantities are given by lambda I to the Q minus 1 divided by norm lambda I Q to the Q. This is not important, the minimizers. The important is the minimum norm. I just wrote it as an extra information there. Okay, so we are able to solve this problem in an optimal way. That's perfect, because now the statement of the theorem of the characterization is going to make much more sense. Before, yeah, just let me give notation. So I'm going to use the notation. So if we have V, a vertex, and if we have U, a child of n degree of V, then I'm going to use this notation lambda V going to U. You know, in the unilateral case, we had all those products of weights. Now we have products of weights over different branches. So that's why I'm defining those things. So this is going to be, I'm starting from lambda U multiplying, and then I'm going backwards, lambda parent of U, etc., up to lambda parent n minus 1 of u. So if you have here u, you have somewhere here v, you multiply with all those weights up to and including this one, lambda parent n minus 1 of u, not with lambda v itself. And this is what occurs after applying the operator n times. Those are the products, and then you sum them up. So that's why we're doing so. Okay, so the theorem says that b lambda is hypercyclic if and only if b lambda, of course, assuming that it's bounded, I'm writing less now, if and only if b lambda is weakly mixing, if and only if the characterizing condition is, by now we can guess it, we need lambda. Okay, let me be more clear. And only if there is one subsequence nk such that for each v vertex, the norm lambda v going to u with u at the children of nk degree of v, the qth norm goes to infinity. Okay, this quantity here that we have inside the norm was the denominator of the optimizing solution before. And we wanted those right inverses to go to 0. So that's equivalent of demanding the denominators to go to infinity. And so this is exactly the condition that all those optimal right inverses should go to 0. And it's to be expected. So after seeing this optimizing problem, this seems natural that this should be the characterization. You get something, the best possible right inverse, and then you demand this smallest right inverse to go to 0. And this should characterize when the operator is weakly mixing or hypercyclic. And the proof of this, I'm not going to do it, but it goes along the lines of the previous, like this implication with the hypercyclistic criterion and everything. At the others, you need some modifications, but yeah, that's it. And some comments here is that, for instance, this condition here depends on P, on the space. So we got something better than what we had before. Also, we are getting many examples that we didn't used to get with normal shifts, but I mean, this involves other notions, so I'm not going to mention. Okay, so this is what I wanted to mention concerning like weighted shifts on trees, just the characterizing condition for hypercyclicity and weak mixing and how to get it and how to motivate it. But still, we have some problems that many natural operators, like what we said, like the read type operators for the invariant subspace problem, they are not shifts on trees still. So those operators, they go like that. This goes here, this goes here. You have, it's a forward shift, and at some point you go backwards. And something escapes and goes forwards. And then in the future, something else comes backwards. And then something goes forward. You see, we have many loops. So it's natural. And many operators are defined like that, pathological and capturing like deep results in operator theory. So it becomes natural to generalize even more the weighted shifts on trees. So one would like to start going towards the direction of weighted shifts on graphs. But this is way too general as a category. So you cannot just leave it as a graph and you don't get any theory from there. I mean, you are allowing pretty much any operator. So what Anton Baranov and Andrei Lishanskii did recently, they invited me with their work, is to start working on lattices. So we have something like some copies, finitely many. So here, let's say m copies of n, the natural numbers, and you have all those points, of course, and you are allowing to go, so the graph goes up and to the right. So the shift goes down and to the left. And you put corresponding weights here. So you have all this lattice. A more general, this you can characterize pretty much with not extreme difficulty. More difficult problem is the following, where you are getting infinitely many copies of the natural numbers. And again, you are leaving the graph, the arrows going right and up. So the backward shift is going to be left and down. And you are putting corresponding weights. Even for the unweighted shift, this is if you don't put any weights, if you just study the unweighted shift, this problem is difficult. But this all those needs here, this is again informal, I'm not saying something very mathematical, I'm just waving hands here, but I wanted to pass to something that we studied recently with Quentin Menet, the generalized shifts. Okay, this is not as general as any graph with loops or something, but it's still more general than the shifts on trees, and it contains some of the lattices, some of the shifts on lattices. So it's a reasonable generalization, and it leaves a lot of, it's a huge abstraction of the shifts on trees. So we are, at some level, we're abstracting a lot the theory, and at some level, we're not including everything, so that we have still some structure there. So what is the idea there? The idea is that on the shifts on trees, we have those generations, and on the usual shifts, we have all those, slots indexed by n. Now we will consider this sequence of spaces, xn from 0 to infinity, a sequence Banach spaces. And then we will consider some operators, linear operators, Tn from 1 up to infinity, where Tn, I want to be from xn to xn minus 1. So the picture that we have is that we have x0, x1, x2, x3, etc. And we have all those linking operators like T1, T2, T3. And all those are like Tn is linear embounded from xn to xn minus 1. We're assuming that. And then we can define at least formally this generalized backward shift B with symbol Tn to act on the sequence x0, x1, x2, etc. as T1, x1, T2, x2, T3, x3, etc. So this is as much as generalization as we can do from the usual shifts and the shifts on trees. It's a pretty much extreme abstraction, because now for each slot here we have a Banach space vector. So it could be an infinite dimensional vector, like a vector lying on LP itself. So each coordinate could be a vector on LP. And then we just have linear operators going from one to another. Of course, I didn't write the spaces here, but one can guess what the spaces are going to be. So the LP of xn is going to be the set of all sequences xn from 0 to infinity, being in the product of the spaces, such that the summation of the norms by now xn p to the p. This is finite. And similarly for C0, you just demand the limit to go to 0. So we have all those spaces, and provided, they are Banach spaces, everything works fine with them. Okay, so we have this formal definition of shift. And before I'm running out of time, so I probably will not have time to mention many things, but I would like at least to see why does this, how much of a generalization it is. So for the unilateral case, my point is that now I would like to see the shifts that we mentioned already, the unilateral normal shift or the shifts on trees or the lattices, for instance, as generalized shifts. How does this notion captures them? So for the unilateral shifts, one has to take just as xn the real numbers, and then the Tn operator from xn to xn minus 1, which is from the real to the real, is going to be Wn times x. It's one-dimensional, so you have only one linear operator, just multiply scalar operator. So you don't really have something. And this gives you the usual shifts. So this gives you a feeling of the extent of the abstraction, that the usual shifts are the one-dimensional analog of generalized shifts, where each coordinate is just one-dimensional. Now, if we take the shifts on trees, Then we have the tree pretty much, and then we have all those generations. So xn is going to be the generation of n degree. So you go at the children of n degree of the root, and you take this. And then you take just the restriction of the shift from this to the previous one. Now, this is not as lean to write down. It's just the restriction of the backward shift from the generation n to the generation n minus 1. But anyway, it's what it is. But like that, we can see it as a generalized shift. And for instance, for the lattices, what I would like to observe is that if you have this lattice that we mentioned before, with infinitely many copies of n, then you can still see this as a generalized shift. And let's say that we take the unweighted shift there, so we don't put any product, any weight on shifting. Then xn is going to be the nth diagonal. So essentially, you have something like that. It's not the main diagonal, it's the other diagonal. So this is going to be the nth space, like I mean the span of the vectors indexed by these diagonal elements, and this is going to be the n minus 1. And what is going to be the Tn? The Tn is going to be the identity plus a backward shift. Because if you see what happens at one vertex, if we start labeling the rows from below to above, so the first row is 1, 2, etc., then what is happening? This comes here, and this comes down here. So one vertex goes directly at the same height, so you have the identity, and one vertex comes from above, so you have the identity plus the backward shift on the indices. So you get that those linking operators are the identity plus a backward shift, which is a class of operators that has been studied a lot in linear dynamics. But I mean, it's interesting that they're not backward shifts themselves. Okay, so I think that I will stop here. I will not have more time to expand on those generalized shifts, but I think I gave some information. Thank you for your attention.